today, and I want to quickly review some things with you before we take a look at your homework. So go ahead and have your homework out now, and your textbooks open to page 52. Homework out, textbooks open to page 52. And I just realized there was one key thing on that we were supposed to cover yesterday, ran out of time on, so that I can understand there's a little issue you would have had on that proof there. But some quick things we want to review. First of all, what do we call a statement that is not self-evident, but has to be proven by a chain of deductive reasoning? Genesis? A theorem, very good. What do we call a statement that's very easy to prove after a theorem has been proven? And you would use the preceding theorem to prove this statement. Audrey? Good. No, not an axiom. A corollary. Corollary, easily proven using a preceding theorem. An axiom, remember, can't be proven. It's so basic. What do we call this process of deductive reasoning whereby the truth of a theorem or the correctness of a construction is established? Ethan? The process of deductive reasoning whereby the truth of a theorem or correctness of a construction is established. Audrey? Genesis? A proof. A proof. We had a 5-letter acronym that we used yesterday, and we said we know that if two figures in general are congruent, that all of their parts have to match. They all have to be equal. We call these matching parts, class, corresponding parts. And since we're dealing specifically with triangles, I had a 5-letter acronym. And what was that 5-letter acronym, Audrey? CPCTE. Let's think about it, class. What does CPCTE stand for? Corresponding parts of congruent triangles are equal. Corresponding parts of congruent triangles are equal. Hey, let me write it up on the board to help Ethan out here just a little bit. Okay, let's say it together, class. Corresponding parts of congruent triangles are equal. And speaking of congruent triangles, we have 3 ways right now to prove triangles congruent. Method number 1, we don't want to use. In fact, you shouldn't ever have to use in this class. And that is where you move one triangle through space and show that it coincides perfectly with another one. We did that once. We don't want to have to do that again. Okay, so method number 2 is the method that we typically would want to use, and that would be, Kendall? SAS, side angle side theorem, meaning 2 triangles have 2 sides equal respectively and their included angles equal respectively. But we said for right triangles, there's another one we could use, Genesis. It's the corollary of side angle side. Ethan? Leg. So basically 2 right triangles have 2 legs equal respectively, then the triangles have to be congruent. That's basically side angle side because what is the angle between the legs in any right triangle, class? The right angle, right? The right angle is between the legs, so leg is basically side angle side because right angles are equal. In fact, that's how we proved the corollary. There's another term that I want you to go and get in terms and definitions. I was supposed to introduce it yesterday, and time just did not permit. So terms, definitions section of your notebook. And it's this word, this idea, identity. This is something that we will use frequently this year. Identity. Any quantity or figure is equal to itself. Any quantity or figure is equal to itself. For instance, if I were to compare Ethan's basketball prowess to some great athlete that I've seen to some other athlete I've seen in the past, if I'm like, you know, Ethan, you remind me a lot of a guy who plays basketball at Grace. Yeah, Ethan. Ethan was his name. And he's, man, is he talented. You dribble just the same as him. Your shot isn't great, but it's a lot like his shot. Okay, of course, you are exactly like Ethan. How long is that line? It's exactly as long as that one. Obviously, anything is equal to itself. And sometimes in trying to get angles equal, or sides equal, or legs equal to get triangles congruent, we may need to say that this line is of course equal to itself. If that line or that angle or something is shared by two triangles at the same time, that's the concept of identity, and that's something that we were supposed to see yesterday in the proof. We tried to get started at the end of class and ran out of time, and it also came up on the homework. So let's take a look at the homework proof. Page 52, number 7. I asked you to copy it down just exactly as it was in the textbook. So you should have copied down this picture. An acute angle, CAB, where CA and BA should have been equal to each other. We should have also had this bisector AD. And then lines were drawn from C to D and from B to D. So two separate lines. You were given, now they put their given up above the sketch, but you were given that AD bisects angle BAC, and you were given that AC equals AB. You were asked to prove two things. First of all, you were asked to prove that triangle ABD is congruent to triangle ACD. I better not find a wrapper on my floor. I assume you won that in another class. And angle B equals angle C. All right, how many got this initial stuff copied down on your paper just exactly? Okay, excellent. Then down below that, of course, two columns. Our first column, class, is a column of statements, and our would be what, class? Yeah, AD bisects angle BAC and AC equals AB, right? Just literally should have copied this down for statement 1. Of course, they gave you reason 1. They didn't need to. You knew it would be the single word given. How many recopied you were given as your first statement, like you should have? Excellent. Number 2, they said that you want to make a statement based on the definition of angle bisectors. Well, Ethan, what is the definition of an angle bisector? What's the definition of an angle bisector? We've got these terms and definitions memorized, correct? We better. So what's an angle bisector? Oh, that's a big problem. You should have looked it up last night. When you saw a definition of angle bisectors, you should have looked up what an angle bisector is. Kendall, help him. What's an angle bisector?
It bisects the angle in half.
Line that divides an angle into two equal angles, or two equal halves. The line that divides an angle, well, AD bisects this angle, BAC. So if AD is the bisector, then it must divide this angle into two equal angles. Remember I said yesterday that numbering angles sure is nice? Let's go and number the angles 1 and 2. Well, if this is a bisector, and if a bisector is a line that divides an angle into two equal angles, then what two angles must be equal, class? Angle 1 and angle 2. Or angle CAD and angle BAD if you want to use the 3 letters, but I am lazy, so I'd rather say 1 and 2. So either angle CAD equals angle BAD, or if you put numbers on them, angle 1 has to equal angle 2. Definition of an angle bisector. How many saw that these two angles had to be equal because of the bisector? Okay, good. Number 3. They said to you that AD is equal to AD. You didn't know this at the time, but what's our reason that AD is equal to AD, class? Identity. And again, that was something we were supposed to go over yesterday in class before you got to this homework assignment. So identity is what we should have written. You had no idea because we hadn't talked about it yet. I'm curious, what did you all write for number 3 since we hadn't talked about identity yet? Audrey, what did you write? No, yeah, that doesn't show why AD has to be equal to its own length, right? Genesis? Which is, you don't even know, you just threw a guess down. By the way, This gives me a chance to address it though. Don't ever write axiom this or postulate this. I don't want numbers. Because again, numbers may vary by textbook, but the truths that we're using don't vary, right? So don't ever use, axiom 7 as a reason. Actually write what axiom 7 says. Or if we've named it something, like theorem 1, we've named the side angle side theorem. Okay, we allow you to use the shorthand there, but we're still not saying theorem 1. We're saying the essence of the theorem, the side angle side concept. All right, so number 4 then, we were supposed to be able to state that the two triangles, ABD and ACD, are in fact congruent already. Well, let's think about what we've got. I've got two sides equal here. Those were given as equal. I've got two angles here. We said those had to be equal because we had an angle bisector. And then this line is equal to itself. So this line of this triangle is equal to the same line in this triangle. So class, we have side, angle, side. So the reason the triangles are congruent? Side, angle, side. And then once you know, listen carefully to this statement. Once you know that two triangles are congruent, then you know that all their matching parts have to be equal. If triangles are congruent, their corresponding parts are equal. That's CPCTE. So since these are now congruent triangles, since we've proven that they are congruent, then that means that these two angles, which are corresponding, angle B and angle C, have to be equal. So angle B equals angle C, and the reason CPCTE. And there we go. Questions on the proof that we did for homework? All right, does it make a little bit more sense now? I know that identity thing was kind of a bit of a puzzler there. Questions? All right, maybe on the back side of your homework, or maybe on another sheet of paper, I want you to draw a triangle that looks isosceles. I am coming back, by the way, to that proof that we started yesterday. We will get to that in just a moment. But first, I want to look at a triangle that appears to be isosceles. And let's go and call it ABC, so that C is the vertex, just so we're uniform in our drawing. Now, you could have drawn a very short, fat triangle. You could have drawn a tall, skinny one. Doesn't really matter how you choose to draw it. I happen to draw tall and skinny, but you draw it however you want, as long as it looks isosceles. Now, we don't trust our eyes, but our objective is going to be in a minute to prove that it is isosceles, and it really helps Genesis if it looks like what we're trying to prove. Right? Like if we're trying to prove something's a right angle and it looks like that, it's going to make our life a little harder, because now we're forcing ourselves to go counterintuitive, where if we draw something that at least is close, we have an easier time with it. So that's the reason why I told you to draw it so it looks isosceles. I want you to draw a line now from C straight down to AB, and we'll call this point of intersection D. Now, it appears, based on the way I drew it, that this is perpendicular, doesn't it? Let's suppose for a moment that it really is perfectly perpendicular. In fact, in your given, we're going to be given triangle ABC with CD perpendicular to AB. Let's suppose that it really is perfectly perpendicular. Let's suppose also, now I'm not sure that it looks like D is exactly the midpoint or not, but let's suppose for a moment that D is the exact midpoint of AB. D is the midpoint of AB. If you draw a perpendicular, what do we call a perpendicular, by the way, in a triangle from vertex to the opposite side? Not the median, the altitude. Okay, so we've got this altitude here, right? CD is perpendicular, and it happens to go to the midpoint. Do all altitudes go to a midpoint? No. By the way, if a line goes from vertex to midpoint, Audrey, what do we call it? A median. So I have told you that CD is both the altitude and the median at the same time. Usually that doesn't happen, right? Usually, if you draw an altitude, it's not a median. Or if you draw a median, it's not an altitude. But suppose, could we draw an altitude that is a median? We could. Let's suppose we really did. Again, even if it's not perfect, we could have made it that way, could we not? I mean, for that matter, draw any line, locate the midpoint using a perpendicular bisector, there's your perpendicular. Okay, now I've got a triangle that has an altitude that is a median, right? It's possible to make it. What we want to prove is that anytime you have a triangle in which an altitude is a median at the same time, that the triangle has to be isosceles. That's what we're going to prove. Prove that triangle ABC is isosceles. Prove that triangle ABC is isosceles. Once you got that down, 2 columns, statements, reasons. Go and get your first statement and your first reason. So we're trying to prove that if you were to draw a triangle in which an altitude was a median, that the triangle would have to be isosceles for that to be the case. Now, before we begin the proof, we like to start with a planning step. What do we call this planning step, Ethan?
Analysis.
And in analysis, I like to think through some things. I'm trying to prove a triangle is isosceles. So I ask myself, what does that mean to have an isosceles triangle? And I answer myself, but I sound a lot like Genesis when I answer myself. And I tell myself, well, a triangle is going to be isosceles if 2 sides are the same length. Very good. You saw how much I sounded like Genesis right there? All right, it's ventriloquism. So if I could get 2 sides the same length, it would be an isosceles triangle. So then I asked myself, which 2 sides should I try to get equal to each other? And I sound a lot like Audrey when I answer myself. If, do we all understand? If AC and BC are equal, it's an isosceles triangle. So you understand then that really my proof is not so much proving this as it is proving this. But then I think to myself, that seems kind of weird. So far, the few proofs we've done, there's been like, what, 4 of them, have always involved congruent triangles. But if you have 2 congruent triangles, what do we know about all their corresponding parts class? They would have to be equal. So if I could get 2 congruent triangles, one triangle has AC in it, the other triangle has BC in it, then maybe AC and BC could be corresponding parts, and then maybe they would have to be equal. So maybe there's a couple of triangles that if maybe I could get them congruent. Do we see a couple of triangles that maybe we could get congruent here, Ethan?
Triangle ADC is congruent to BDC.
Okay, so he's saying ADC, that's this right here. If we could get it congruent to, he said BDC, which is this one here. If these 2 triangles were congruent, would these 2 lines be corresponding parts class?
Yes.
So then they would have to be equal, right? So do you see how now my proof is not so much about proving this as much as it is trying to get congruent triangles. Do you see how the thought process works? Well, how can I get congruent triangles? Well, there's a couple of ways I can get congruent triangles. Well, there's one way I don't want to use. That's the whole move through space line, everything up, show it all. Don't want to do that. But there's 2 good ways. Kendall? Or? Right, side angle side or leg length. Be careful. CPCTE does not prove that triangles are congruent. By the way, let me say this again, because students get this mixed up. CPCTE doesn't prove that triangles are congruent. Because what does it stand for? Corresponding parts of congruent triangles. It assumes congruency. You would have to get triangles congruent first, right? Now, leg though, Genesis, is only something we could use with what kind of triangles? Good. In the leg-leg corollary, it specifically says two right triangles are congruent if blah, blah, blah. Two legs are equal respectively, right? So leg-leg only would apply to right triangles. Genesis, are these two triangles right triangles? Is there any reason to think they might be? What is it about this picture, or about the given rather, that tells me these might actually be right triangles? Ah, perpendicular. Remember I mentioned yesterday clang statements, clang words? That when you hear the word or you see it in the given, you're like, oh, I know what to do there. You know, it's like ring bell, drool. Don't ring bell and drool. But when you see perpendicular, clang, we should be thinking, ah, I know what perpendicular lines do. They give me right angles. So if these two lines are perpendicular, they give me right angles. Where are the right angles, Genesis? At D, right? Now, what you really mean is CDA and CDB are my two right angles right here. But I'm too lazy to write CDA and CDB. So you know what I'm going to do instead, class? 1 and 3. And
What?
You can number whatever you wanted. We'll go with 1 and 2. That would really frustrate some people if I did 1 and 3 for my angles. And Kendall's looking at Audrey. But we'll go 1 and 2 here. And I know for a fact that angle 1 and angle 2 are in fact right angles. How do I know they are right angles? Listen, because I have perpendicular lines. Whenever you hear yourself saying in your mind, because I have this, you usually mean definition of, right? Because I have perpendicular lines. Well, what's the definition of perpendicular lines? Lines that meet to form right angles. So because of the definition of perpendicular lines, I know I must have right angles. Let me spare that jump. Sorry, making the camera jump everywhere here. Nice. Make sure that I get everything in the screen there. Definition of perpendicular lines tells me I've got right angles. Now, if I have right angles, or let me just say if I have a right angle in a triangle, then that triangle has to be a right triangle, does it not? How do we know a triangle has to be a right triangle if it has a right angle in it?
What?
How do I know a triangle is a right triangle if it has a right angle in it? Because that's the definition of a right triangle, isn't it? A triangle with a right angle in it? So I know that triangle ADC is a right triangle, but that's not the only one. What else must be a right triangle?
CDB.
CDB or BDC. Triangle ADC and triangle BDC are right triangles. I know they are because that's what a right triangle is. A triangle with a right angle. It's a triangle. It's got a right angle. It's a right triangle. Definition of right triangle. Again, when you find yourself, but because it has to be, that's what a right triangle is. Definition of right triangle. Starting to see when to use definitions. Right, when it defines what something is, that's your definition of. So I've got two right triangles, so now leg is very much an option. By the way, you cannot use leg if there's not a statement that says they're right triangles. Think about it. You try to prove triangles are congruent because two right triangles are congruent if, and they turn out not to be right triangles in the first place. True story, it's happened not often. But ever watch maybe a trial on TV or something, maybe a TV show, and of course not everything in there is exactly accurate, but what's the first thing they always have the defendant do? Would you please state your name for the court? Kendall, we have her state her name. That's the first thing we do. Because the court is now going to try to prove that Kendall did this thing. But if they never prove that she's Kendall, they haven't proved that she did it. They can bring all this evidence against Kendall. And Kendall gets off scot-free if they don't prove she's Kendall. Does that make sense? We can prove all this stuff about right triangles, but if we don't state that these are right triangles, then it doesn't apply to them. That makes sense? So you have to state, in order to use leg-leg, there has to be a statement in there that says they are in fact right triangles in the first place. But we stated it, so now we can use leg-leg. So to use leg-leg, you need two legs equal respectively, right? Well, nowhere in my proof does it say that two legs are equal respectively. Let's think about it. In ADC, what are the two legs here? Audrey? AC is not a leg. In the right triangle, ADC, what are the two legs? What is a leg in a right triangle? You have to know your definitions. It's not just a side, it's a special side. What is a leg in a right triangle? Helper Genesis. You have to know your terms. The sides that make the right angle. Okay, Genesis, which sides make the right angle in ADC? CD and AD. Those are the two legs, okay? Back to Audrey for redemption. In BDC, what are my two legs? CD and BD. Those are the legs, okay? So I need these two legs equal to those two legs. If I can get these two legs equal to these two legs, I'll have leg-leg. I'll have congruent triangles. And then two lines will be equal by CPCTE. And the triangle will be isosceles. Do you see how line on line proving it? Here's the question, how can I get some legs equal here? Which leg do you think AD would be equal to? CD or BD, class? BD. Probably BD. How could I get AD and BD equal to each other? Is there something perhaps in the given that would tell me that AD and BD might be equal? D is a midpoint. So what's a midpoint, Genesis? It's a point that divides a line into two equal parts. Wait, so if AB is a line and D is a midpoint, then these have to be equal parts, don't they? Because of what a midpoint is, or we might say, because it's a midpoint. It's what a midpoint does. It divides a line into two equal parts. That's the helper class definition of a midpoint. So yes, I do know number 4 that AD is equal to BD. They have to be equal based on the definition of a midpoint.
I'm sorry to get this.
All right, so there's, hey, look at that. That's a pair of legs. Equal right there. I'll put a little L next to that. Not for loser, but for legs. Okay? So now I need to get the last legs equal. So in this triangle, I've got this leg CD, and I guess it's got to be equal to this leg in this triangle, CD. How could I get CD equal to CD? Identity. It's the same line. Of course it's equal to itself. So number 5, CD equals CD by identity. So now I have leg class, which means my triangles have to be congruent. Number 6, triangle, how do we want to name our first triangle? Ethan?
ADC.
Triangle ABC is congruent to triangle. Now here's where we have to be careful. We have to make sure corresponding pieces line up. What corresponds to the point A?
B.
B does. These two vertices match up. What corresponds to this vertex here, D?
D.
The other D, the other side of D. And of course, corresponding to C, the other side of C. And they're congruent. How do I know they're congruent? Leg-leg. They are right triangles. We proved that. We stated and proved that they're right triangles. And they got two legs equal. Therefore, they're congruent by leg-leg. And if they're congruent, then all their corresponding parts have to be equal to each other. Now, I don't care about all their corresponding parts. I'm going to care about two corresponding parts in particular, Audrey. AC and BC. I want these two parts that are corresponding to be equal to each other. How do I know that those two corresponding parts of the congruent triangles are equal, Audrey? Yeah, that's what corresponding parts are. That corresponding parts of congruent triangles are equal, CPCTE. And if, we've been looking at these as two different triangles. Look at it as one big triangle again. If in one triangle, two sides are equal, the triangle has to be, class, isosceles. So therefore, number 8, we get what we wanted to prove. We're going to write it down there. A triangle ABC is isosceles. What do you suppose the reason might be? How do I know ABC is isosceles? Do we know it's isosceles? How do we know?
Okay. EC equals BC.
Has 2 equal sides. That's the definition of an isosceles triangle. So your reason? Definition of isosceles triangle. We know it's isosceles based on the definition of what an isosceles triangle is. A triangle with 2 equal sides. And we proved that 2 sides were equal. So it has to be isosceles. And there's our proof. Ethan says he's starting to get the hang of it. The others said he's starting to feel like, okay, I'm starting to catch on here. Let's do another one. Find that proof we started yesterday in our last lesson. Find the proof we started yesterday in the last lesson. Told you, put it on a piece of paper, you will not lose. So if you lost it, then you disobeyed and you get a detention. Okay, I'm just public humiliation, maybe. Public flogging has been outlawed, so I guess that's not a good.
Oh man.
I know, I was disappointed too. Just kidding. All right, so we had, it was this X, A, Y, and we had AB bisecting, and we had this point P that we had picked. And we had lines going from XP to YP. I think this was the picture. And we said that XA and YA were supposed to be equal. So I said draw 2 lines that look like they're equal, that make an acute angle with each other. Draw to the best of your ability the bisector of that angle. Pick a random point in the bisector and draw lines to that point. So did we get as far as the given? We haven't written it down. Okay, so given. Well, the first thing I told you was to draw 2 lines equal, XA and YA. So XA equals YA. Go and draw your 2 lines so they are equal, XA, Y. Now again, we could have made them exactly equal with our compass. We could have measured one, measured the other, and erased a little extra. We don't trust our eyes anyway, so we don't care that much. But we got 2 lines that are equal. We also drew AB bisects angle XAY. AB bisects angle XAY. And then we picked a point on AB. Well, we picked any random point. It's not a special point, it's just any random point, so who cares? So P is any point in AB. What we want to prove is if you take any acute angle and bisect it, any acute angle with equal sides, and bisect it, then any point in that bisector is going to be the same distance to the ends of the sides. We want to prove that XP is equal to YP. Not proving that XP is equal to Windows 10, proving that XP is equal to YP. That was for Chris. All right. All right, who's not here? He's watching the video later, though, I'm sure. Ms. Twist, I sent the link to Mom, so she will make sure he watched it later. All right. So, you want to get down your first statement, first reason, get all that set up. I see a clang statement here. A clangy word. A word that means something to us in our given. What word should really mean something to us here? Bisects. This isn't just any word. It's not that AB is just some random line. It's not a random line. It's a very special line. It's a bisector. And we see bisects, we should think clang. What should we be thinking about a bisector of an angle?
Two equal angles.
2 equal angles. That's what we should associate. Bisector, clang, 2 equal angles. What are the 2 equal angles?
AYP and AXP.
AYP This angle here?
PYA and P.
PYA? Yeah, this angle here?
Come on.
PAY, this angle here?
Yeah, no.
Okay, and? PAX, this angle here. This is why I like to number angles. Put a 1 and a 2, and 1 and 2, right? So what should we state for our second statement? Angle 1 equals angle 2. How do I know those two angles are equal? Good, because we have an angle bisector, and that's what an angle bisector does. That's what it is. It's the definition of angle bisector. You're catching on? Good. This is one of the things I like to do to start out our proof, is look for something clangy in the given. Something like a midpoint. Clang, 2 equal segments. Bisector, clang, 2 equal angles. Perpendicular, clang, right angles. I like to look for clangy words. Unfortunately, that's the only one. Now let's look at what we're trying to prove. We're trying to prove that these two lines are equal to each other. That's kind of weird. Again, so far, all of our proofs have to do with what class? Congruent triangles, right? Getting triangles congruent. But it doesn't say anything about getting triangles congruent.
Just proof XP equals YP.
Yeah. But if I did prove that a couple of triangles were congruent, would that help me to get XP and YP equal? How?
Two triangles.
Because if two triangles are congruent, then their corresponding parts have to be equal by CPCTE. In fact, most of the time, I won't say most, oftentimes, if you're asked to prove a couple of lines equal or a couple of angles equal, the best way to get that done is to get congruent triangles first and use CPCTE. Write that in the class notes section of your notebook if you would. Go ahead and jot that statement in the class notes section of your notebook. Maybe put a star next to it. Often, the best way to prove lines or angles equal, often, the best way to get lines or angles equal is to first get congruent triangles and then use CPCTE. Often, the best way to get lines or angles equal, or prove lines or angles equal, is to first get congruent triangles and then use CPCTE. So it says prove these two lines equal. But in my mind, I'm like, well, I want to get a couple of congruent triangles, because if top triangle and bottom triangle are congruent, then of course these lines are equal by CPCTE, right? Now, I've got some ways to prove triangles are congruent. Audrey, what are my top 2 ways to prove triangles congruent? Or, but remember, leg is special. It only applies to right triangles. Do I have any indicator of right angles or right triangles here? This time, no. There's no perpendiculars. There's no right triangle. So let's just go with side angles side. So let's look at what we got. Do I have any sides equal so far, class? Yeah. XA and YA. They were given to me as equal. Do I have any angles equal?
1 and 2.
Yeah, I just showed that 1 and 2 are equal. So somewhere, there's got to be some equal sides to finish out side, angle, side. Well, let's think about it. There's a logical order here. Side, angle, side. So in the bottom triangle, I want PA, right? But let's look at the other triangle. Side, angle, side. Okay, so in the top triangle, it needs to be side AP. So how could I get AP in this triangle equal to the PA in this triangle? It's the same line. Of course it's equal to itself by class identity. Anytime there's a shared line or a shared angle, often it helps to say that that line equals itself by identity. And that's something you'll get in your notebook here, Chris, in just a minute, or later on when you go back and watch the video. But AP equals itself by identity. Well, look at what I've got then. That means these two sides are, two sides, right? Side of this equal to side of that. These two sides are equal. Well, look what I got, class. Side, angle, side. So my triangles are, in fact, congruent. Number 4, what 2 triangles are congruent, Kendall? triangle XAP is congruent to triangle
YAP.
good YAP. X and Y correspond to each other, A and A correspond to each other, and P correspond to each other. So making sure they line up. And these triangles are congruent, class. What's my reason?
CPCT.
Side angle side,
Oh,
right?
yeah.
The side angle side theorem. If two triangles have two sides of one equal to two sides of the other, and the included angles are equal, then the triangles have to be congruent. And now that the triangles are congruent, what does that mean about XP and YP?
XP equals YP.
They have to be equal because they are corresponding parts of two congruent triangles. In other words, CPCTE. I should say in other letters. CPCTE, so XP equals YP by CPCTE. And we're done with the proof. Just 5 steps. Questions on this? So you see the basic process here? Get congruent triangles. And if you need to, you can get lines equal, angles equal, whatever by CPCT. But it's kind of a process here. Now, I told you yesterday that the more facts you have memorized, the more tools you have in the toolbox, the easier it is to do proofs. So I want to give you another tool. We've been using side angle side and leg leg, but there's other tools you could have as well. Turn to the Theorems Corollaries section of your notebook. Theorems Corollaries section of your notebook. Down below where you wrote Corollary 1-1, I want you to write Theorem 2. Theorem 2. Theorem 2 says this: two triangles are congruent if one side and the two adjacent angles of one triangle. Two triangles are congruent if one side and the two adjacent angles of one triangle are equal respectively. Two triangles are congruent if one side and the two adjacent angles of one triangle are equal respectively to a side and the two adjacent angles of the other. Two triangles are congruent if one side and the two adjacent angles of one triangle are equal respectively to a side and the two adjacent angles of the other. Equal respectively to a side and the two adjacent angles of the other. In parentheses, ASA. This is our angle side angle theorem. Once you have that down, turn to the proofs of theorems corollaries section. Turn to the proofs of theorems and corollaries section. And at the top of a new sheet of paper, just write Theorem 2, capital ASA. Theorem 2, capital A, capital S, capital A. Top of a new sheet of paper, Theorem 2, capital A, capital S, capital A. For sake of space, I don't want to erase the theorem we wrote out. And go with this. If you would, go and draw a couple of triangles that, to the best of your ability, look congruent. And we don't trust our eyes, so if they're not perfectly congruent, doesn't matter a whole lot, but they can look roughly congruent to each other. Go and call the first triangle ABC, and let's call the other one XYQ. Did you write Z or Q?
I wanted to write Z.
Okay, we'll put Z. Now she makes me feel bad. She's like, I'm just going to be so sweet and submissive, and you said Q, so I'm going to put Q, even though everything in me wants to put Z, Mr. Nadasky. And now I'm like, gee, now I feel like a jerk. Okay, let's put Z. Anyway, if you'd be like, nah, I put Z. They're like, okay, I'm going to leave my Q up there. All right, anyway. So here's what we're going to be given. We're going to be given that one side of this triangle equals one side of that one. For sake of ease, let's just go with the bases. But it really doesn't matter which sides we choose. A, B, and X, Y. And then the two adjacent angles to whatever side we picked. Well, the adjacent angles to AB are angle A and angle B. Have to be equal respectively to the two adjacent angles at XY, which would of course be X and Y. And we're going to prove that if I just know this much, that the triangles have to be congruent. So, for our given, we're given triangle ABC and triangle XYZ with AB equal to XY, angle A equal to angle X, and angle B equal to angle Y. Triangle ABC and triangle XYZ with AB equal to XY, angle A equal to angle X, and angle B equal to angle Y. We want to prove that triangle ABC equals triangle, or is congruent to, triangle XYZ. We want to prove that given just this much information, that triangle ABC has to be congruent to triangle XYZ. Once you have that down, 2 columns, statements, reasons. Once you have that down, 2 columns, statements, reasons. Now, the good news, I do not have to show that these 2 triangles coincide throughout. I can use side angle side to prove them congruent to each other. Notice I've already got these 2 sides equal, and I've already got these 2 angles equal, or these 2 angles equal, really doesn't matter which ones. So you realize if I can get these 2 sides equal, I've got side angle side. Or if I can get these 2 sides equal, I've got side angle side, right? So the crux of the proof then is somehow, some way, getting that side and that side to be equal, or this side and that side to be equal to each other. Make sense? How? Well, what would make line segments equal? If their endpoints can coincide.
And AB equals XY, so they must coincide.
They do, yes. I'm saying AC and XZ. Guess what we're going to have to do?
Move it to space.
We're going to have to pick the one up and drop it on the other and hope that somehow, some way, not hope so, no, but make sure the lines intersect. So let's start by, again, putting just one point, one vertex, on top of one vertex, and lining up this side along this side. Place triangle ABC onto triangle XYZ so that A falls on X and AB falls along XY. And I'm just going to say move through space because I'm too lazy to write out a geometric figure may be freely moved through space without any change in form or size. Let's do move through space. Because we're lazy. Place triangle ABC on a triangle XYZ so that A falls on X and AB falls along XY. But, as Chris pointed out, these are equal line segments, correct? And therefore, if one endpoint coincides with the other, and the lines fall along each other, then the other endpoints must coincide, correct? So therefore, I do know, not just that AB falls along XY, but that B must coincide with, say with me, Y. B coincides with Y. It has to, because the line segments are equal. Therefore, the endpoints can be made to coincide. That's the of equal line segments. And furthermore, if these 2 points coincide with each other, so A is right here, B is right here, I have an angle right here that's equal to this one. If these angles are equal, well, what are equal angles? Angles whose sides can be made to coincide. So since AB already coincides with XY, this side, I don't know how long it is, has to line up with this side that I don't know how long it is. But the sides have to lie on top of each other to some extent, correct? They have to follow along each other. Similarly, since this angle equals this one, and this point now coincides here, and this line now falls along here, then BC must fall along YZ somewhere, correct? So because we have equal angles, AC must fall along XZ, and BC falls along YZ. They have to. We have equal angles. Sides coincide. They fall along each other. That's the definition of equal angles, based on the definition of equal angles. Move this out of the way for you. But here's the thought. AC now falls right along AZ. BC falls right along YZ. These lines line right on top of each other, and two lines can only intersect at one point. So if XZ and YZ intersect at Z, and these two lines AC and BC now lie right on top of them, they can only intersect at the exact same point, correct? Therefore, C must coincide with Z. C coincides with Z because two straight lines can intersect at only one point. Now what that means, B coincides with Y. C coincides with Z. The endpoints of BC coincide with the endpoints of YZ. If line segments' endpoints can be made to coincide, then the line segments must be equal. So therefore, number 6, I'm going to write it off to the side here, BC must equal YZ. BC equals YZ, based on the definition of equal line segments. And if that's true, I have sides equal here, angles equal here, and sides equal here. I have side, angle, side. So number 7, the triangles have to be congruent. Triangle ABC is in fact congruent to triangle XYZ by side, angle, side. And so we've added another tool to the toolbox. Now we don't have to rely on side, angle, side for all of our proofs. We could go with angle, side, angle. And starting tomorrow, we'll use that occasionally. Now, homework this evening, we'll have to save the corollary for tomorrow, unfortunately.